Okay, let's try this. So we know we want to figure out what the force is going to be. All we have to remember ever is that stress is equal to whatever modulus you're working with. So in this case, it's going to be a Young's modulus, right? So it's going to equal y times strain. Stress is always going to be considered, has units of pressure. So it's always going to be force divided by area. And strain is always going to be unitless. Strain is going to be, in this case, it's going to be, it's going to be stretch divided by original length, right? The amount that the length has changed divided by the final length. So we'll call that delta L over L, right? For what would the strain look like for a shear modulus problem? It's going to be, so this is how much did the length change divided by what the original length was, right? What would the strain be for a shear modulus problem? Like
how far it bends?
Yeah, okay, so we call this delta x, how far it bends compared to divided by what?
How long?
Say it again.
It is.
How long it is, by the length of the, right, good. So that would just become a delta x, and that would become a shear modulus instead of a Young's modulus. But it'd be the same thing, right? What we're going to learn today, or I mean, but we're going to go through a couple sample problems today on bulk modulus, where we're talking about what forces are involved when liquids or solids expand, right? So this is going to be a delta V, and that's going to be a V, right? How much does the volume change compared to what the original volume was, and that's going to be a capital V for bulk modulus. Same problems though, really, all the same problems. So on this one, if we want to find, we're trying to calculate the force that has to be applied to the piano string, piano wire, to stretch it by that much, right? Yeah, okay, so we're solving for F. So F would just equal y delta L A all over L, right? Would agree, and all this really is just a matter of plugging and chugging into a calculator. So let's do this. Pull this up on the calculator. Oh, it's over here. Okay, so Young's modulus, and on this problem it was given to us as 209 times 10 to the ninth. So let's put everything on the top in one set of parentheses, right? Let's do all this in one fell swoop. So we get 209 e to the 9 standard units times the change in the length. We're going to stretch it by 4.73 millimeters. How many places do I move the decimal to make that meters? 3 to the left, good. So times, oops, I don't want to do that though, times 0.00473 times the cross-sectional area. Okay, so it has a diameter, the wire has a diameter of 0.851, so we need to multiply by pi times the radius squared, right? So the radius, we're going to put the radius in parentheses because we have to calculate the radius in our big calculation here. So we want r, pi times r squared. How are we going to get r from this?
Divide by 2.
Okay, so we divide by 2. Same thing as multiplying by 0.5. So 0.5 times this, right? Okay. What else? So that gives us the radius in millimeters, right? Got to go to meters, so I'm going to have to multiply by what? this is number of millimeters. Good, multiply by 1,000. I got to make it much smaller, don't I? Because meters are big, millimeters are small. So I'm going to have an even smaller number of meters. Times 0.001. Okay, and then I'm going to square that whole thing, right? Because that's my radius. And then I'll close the top. Okay, everybody with me? I'm just going to divide that by, on the bottom, all we have is the length. And that's already in standard units, 1.339. Okay, and what's that give us? 420, and that's off. It's supposed to be, is that off?
That's what it got.
Yeah, that's the right answer.
Yeah. Those are just misplaced somehow.
It could be, I'm thinking, was off by exactly how much?
Well, I was,
Because it was the right number, it was just off by a factor of 10, wasn't it? So those are usually easy to find.
I don't know where it could be because I had the millimeters correct.
Did you square it? In the area?
The millimeters correct in both.
In both.
Man, I don't know. Did you think that was in millimeters and change that or something?
Mine was 1.36.
It's gotta be, it has to be, if it's off by exactly 1,000, it's
Wait,
gotta be that.
your answer was 422.
Was 420.
I had a different question. Your answer was 420.
What was, I can look at, this was from here, so maybe it's.
But never mind. This is.
So the right answer was supposed to be, maybe that was 420 was supposed to be the answer. 1, 2, 3. God, that's what it's got to be, Nick. It's got to be one of the conversions because it's off by exactly 1,000. It just has to be. There's no other way that one could.
Wait, isn't it 10,000?
Does that explain?
It's not 10,000.
What's that?
It's not off by 10,000.
420, 1, 2, 3. Oh yeah, it is. It's off by 10,000. So yeah, I don't know what that is. I don't know what that is.
It's the same thing incentive though. It sounded like the same thing. Like he would just move the decimal at the end of the question. I watched him do it.
It worked.
You know, I know. I mean, it works, but I don't know why that happened.
I don't either. Did you put in the wrong Young's modulus maybe or something?
I don't know. I thought I was just not converting the millimeters or whatever.
Okay.
But I wasn't really paying attention. I was getting them right. So.
Okay. Well, we'll look at one. When we're done here, I'll look at one of those. I'll look at yours, Seth, and make sure.
I don't even know where that was.
Okay, so what I want to look at today then, let's take this example.
I mean, not if you're right.
Mr. Oya,
Yep.
if we have time, could you go over the question with like the power pole with the cord?
Yeah, you want to do that one?
Yeah.
Okay. Yeah, that'd be good.
5.3.
Yeah, that's a tricky one, huh? I was pretty proud of that one. So that was a shear force one. That guy. Ooh, man, look at all that text. Ooh. Don't you hate when you see problems like that where it's just all that writing? Oh, man.
Don't you get tired of writing?
No. Never get tired of physics. Ah. Okay, let's look at this one. Yeah, there's a lot going on with this. So we got this 12.6 meter high power pole on level flat ground. It's connected at its top to two sections of power line that form a 90-degree angle seen from above. So in other words, if this is the power pole, right? Here's the power pole, they're standing straight up. There's going to be two sections of line that are coming in like this, right? So seen from above, the wires are connecting to the pole, making a right angle. That make sense? Okay? So we got that. The tension in each power line is given to us. Okay, now, each power line sags so that it makes an angle of 78.5 degrees with the pole. So let's try to draw this picture, first of all. Pictures in physics are really important. So here's the pole, and we've got these lines that are connecting to the pole. Like that, and the lines make a right angle, right? But the tension, the way the lines connect to the pole, so here's one of the lines, there's the tension vector pulling on the pole. It forms a 78.5 degree angle, right? So when the lines, everybody see what that means? When the lines are connecting to this thing, they're drooping down, so that as they leave the pole, they're drooping down at an angle of 78.5 degrees with respect to the pole. Okay, so it's only going to be like 11.5 degrees relative to vertical or to horizontal. Okay? All right, so back to business here. They give us the moduli for all these here. They're telling us it's a wooden pole. Give us the diameter. The wood can be considered to be 46% as strong as hardwood, and hardwood's on our chart. Okay. Answer the following questions. So what's the tension in the power lines? What the tension in the power lines causes the pole to bend so that the top of the pole moves horizontally by how far? Okay. First, we got to know what's the tension in the power lines. So before we do anything else, this becomes a dynamics problem, right? We have to resolve the forces. Okay. So seen from above, if we look from above, here's the pole. There's the pole, and here are the tension vectors pulling away, right? Okay, what could we do if we're looking straight down? We might as well combine both of those into one, right? Add them up tip to tail. Everybody agree? So we can write that like if that's t and that's t, what's going to be the length of that vector? So in other words, we could trade this, instead of having two separate lines pulling at a right angle, we could trade that for one power line pulling right in between the two with what total tension? That's just a 45, 45, 90, right? So if a leg is T, square root of 2T, good. So you know that there's the total, the net force vector acting on that pole, right, due to the tension. Okay. The pole's going to push back, right, but that's the force acting on the pole, right? It's acting, instead of this, instead of having our pole with the two vectors pointing out at a 45, we're going to trade it for one line that's pulling out a little bit harder, right in between the two, right? Okay, so then if we look from the side, what does this look like? So if we look from the side, then we've got our pole. And up here at the top, we've got this vector that's now 2 square root of 2 times t at 78.5 degrees, right? We know what the tension is. They give that to us. We can plug that in later. It's 503 newtons, right? And so we can take this sideways force and we can break it into components, right, based on this angle. So what are those components going to be? There's going to be a downward compressional force and a horizontal shear force, right? So how am I going to get those? What's going to be the magnitude of this one? So this is like my theta, right?
Square root of 2 sine.
Sine, good. Sine, I'm just going to call it theta, so I have to write that angle down every time, right? Pointing to the side. What's going to be the magnitude of the compressional force then? The component of the tension that's pushing down. Yeah, square root of 2t cosine theta, right? And so if I want to know how far this thing's going to bend, well, there's the applied force, isn't it? Right? That's the amount of force that's applied sideways. And so now all I've got to do is just use my stress equals shear modulus times strain, right? So F over cross-sectional area equals shear modulus times delta x, how far it's going to bend, divided by the length of the pole, right? And so if we solve that we're trying to find out how far it moves, so we're just solving for delta x, aren't we? Right, everybody see that? So delta x then would just equal, if I multiply by the reciprocal of s over L naught, I get F L naught over AS. So we can plug in numbers for that. Okay. And there's the force, right? Square root of 2 times t. So let's plug all that stuff in on our calculator. Questions so far? Is that making sense? So this time let's just calculate everything line by line so we can check. So what's the force control? Force is the square root of 2 times, actually this is the force, right? Square root of 2 times t sine theta. That's, I'm going to change that. That's the shear force. So that's what's going there. Only the horizontal component of the combined tension of the two lines. Okay? So we get square root of 2 times the tension, what was it, 513? 503, something like that. 503. Times the sine of 78.5 degrees. So sideways force is almost 700 newtons. Horizontal. That's our one. Okay. So now what? So we got to find. So there's F. What about the initial length? We know. What about the area? Let's calculate the area. Okay. So what did it tell us about area here? It's
16.3 centimeters.
oh, in diameter, right? So it's going to be 8.15 centimeters in radius, right? So the area is going to be point 815, is that right? 0.0815? Right, if I turn that into, because that makes sense? This is 0.163 meters, agreed? So half of that is 0.0815 squared times pi. So there's the cross-sectional area in meters. Okay. Now, what about this, this is the part that might cause you to scratch your head a little bit here. What about the shear modulus? What are we going to use for shear modulus? Okay, good. This is the percentage. We said this is 46% as strong as hardwood. So we got to, what is the shear modulus for hardwood? So it's 0.46 times, what was it again, Laura? 10 times 10 to the ninth. Okay, so there's our shear modulus for our wood. And then the only other thing left is just a given. That's just the length of the pole, which is 12.6 meters, right? So now we'll just plug all that stuff into our formula here and see what we get. So we want the quantity force, which is this guy, times the initial length, which was, how long was this one? Remember? I'll forget. 12.6 standard units in meters divided by the quantity area. So there's our area in meters. Times shear modulus. And shear modulus was right there. And we get that. Not very much. So delta X, if we round that, that's going to be, how many, we had 3 sig figs, didn't we? Which was all given in terms of 3 sig figs?
Yeah.
What about the shear modulus? Was that given to 3? Well, I think it's, we would assume it's to 3. I think the answer assumes it's to 3. So it's going to be 9.15 times 10 to the negative 5. So that's 1, 2, 3. So what is that? We got centimeters, so we got millimeters, we got about almost 1/10 of a millimeter is how far it goes.
What was the shear modulus of the, without the percentage?
It was 10 to the ninth.
Just 10 to the 9?
10
Oh, 10 times 10 to the ninth. Ooh, okay, that was wrong. So we got to go up.
What?
It was 10 times. See, this just says 10 to the ninth.
It was
No, that
10
says
each
10
time,
times
doesn't
10
that
to the ninth.
count as?
It's 10 to the
Oh,
10.
you're right. You're right. Never mind. Yeah. You're
Shouldn't
right.
it be? 'Cause it's
Yeah, we're
10.
good. Okay. So that's what we should have gotten for that one. Should we check it and make sure
Yeah.
for that first part?
So it should be 10 to the 10.
So
Yeah, by 10.
9.15 e to the negative 5. Okay.
Is it just 3 sig figs?
3 sig figs. Looks like everything's 3 sig figs.
Can you check just one part of it?
Yeah. Well, no, I can't. But should we? I'll just check it and we'll see what the other. See if. So what was it again? 9 point. Remember? Oh, I can't remember. 9.15 e to the negative 5. Okay.
And just, square root of 2 t sine beta would be the horizontal tension.
What's that?
Square root of 2 t sine beta is horizontal tension for those answers.
Yeah. Yeah. Meters, right? Meters. Okay, so there's part 1. Okay, what about the compression in the pole? That's pretty simple, really. We don't have to change very much of that, do we? The only thing we're having to change for the compression is down here in our stress versus strain. instead of this being a shear modulus, it's a Young's modulus. And instead of that being delta X, it's changing length, it's delta L, right? But otherwise, all that stuff is the same. So if you, all the thinking that we did before applies, if we're trying to find the compression of the pole, one thing we have to change is this equation just becomes, this one just becomes F over A equals Young's modulus times delta L over initial length, right? And so when we solve for delta X, it's the same kind of calculation we did. Gosh, what's this thing doing today? We just get delta L equals F times initial length divided by area times Young's modulus. And we can put all that stuff in too, right? So the only differences are the modulus is Young's modulus, and the force is going to be the one that we calculate using cosine instead of sine, right? So we can probably do all this just right on our calculator. So let's go up. We want to change this top one. That one we want to change to a cosine. So there's 140, about 142-ish. That's the compression force, right? That's the component of tension that's compressing the pole. And then, are you in degrees mode, or are you? Say it again, Laura. That's why. There you go. Yeah. Okay, and then what's the Young's modulus for hardwood? 15 times 10 to the 9th. So we can take this last one and we can just trade the 10 for a 15. Okay, so there's Young's modulus for our pole. And so all we have to do then is just take our force, about 142 newtons, times the length of the pole, which was, what was that? 12.6, right? Divided by the cross-sectional area, which was, we can grab it right up here, that was, well, I guess we can't.
It's gonna be up farther,
Up further, can we see it somewhere up there?
probably.
Right there. That's it right there, isn't it? Or is that for last problem?
Isn't it the same?
Oh, it is. That's it right there. Yeah, so that's it. So we got that problem for that guy. I put it in parentheses. So that's the cross-sectional area. We already did that calculation.
It should be 10 to the 10th, not 10 to the 9th, because it's 10 times 10 to the 9th. This shear modulus.
Can you just did
10. Right, but isn't that, when you use the E notation, isn't that saying 10 times 10 to the 9th?
Isn't that 10 to the 9th?
10 times 10 to the 9th is,
Oh, I know it.
it's the same thing I was thinking too. Yeah, I was,
Mr. White, I think you just did something. You didn't insert.
oh, I just inserted the wrong thing.
You hit second parentheses.
There we go. That's what I
But I
wanted.
think you also moved the decimal over a place.
I did? I don't think so.
Like this.
I think the decimal's fine. Yeah, 0.02.
Okay.
That's right. And then times Young's modulus, and we already calculated, that is,
Isn't it about?
down here further, yeah. So there's Young's modulus right there, isn't it? 15 times 10 to the 9th. So times go up and grab Young's modulus. Close the parentheses. Now, what do you think? Is this going to be greater or less than the... Quite a bit less, because it's a lot stronger compressionally, and there's a smaller component of the force compressing it. And so, what do we get? 1.24 times 10 to the negative 5? Boy, that doesn't seem like that's that much smaller, does it?
I bet.
Is that what you got? You got a lot less than that?
Oh, to the negative 5, actually. Well, I have it
That's about
right.
the same amount that I got.
Okay. Okay, we'll try it. 1.24 e to the negative 5 for this guy. Times 10 to the negative 5. That was meters. Okay, so we check that and just see. I'll put in some dummy answers here, and we'll just see if we got those parts right. Oh, no, we got nothing. So what's this saying it's supposed to be?
It doesn't show you that.
Oh, it's not showing me.
I don't know how I'm doing.
Here, I'll just do that. No, I had negative 5, and this says negative 6. I had both of those to the negative 5. So I'm off by 10, so I must have done something really dumb.
Or the system's flawed and move.
Everyone should just get this problem right.
Did you convert the centimeters to meters when you did?
I must have done something.
Here, Mr. Oy, did you change the centimeters to meters before
Or they both to
or
the
after
negative
you
6, though.
squared?
I know, there's got to be something.
Mine are to the negative 4 and the negative 6.
Man, I don't know what's going on with this. 46. Okay, I feel like I had to do something with my conversion. Do you guys kind of get a sense, like when you're doing these things, you want to see, it's always a good idea to compare what the right answer is to what your answer is. And if it's off by a factor of 10, almost for sure there's some conversion error, right? So I think I must have converted, I think this area must be wrong that I calculated up here. Let's go up and see what kind of boneheaded thing I did this time. Pi r squared. So is that the correct radius?
What's the diameter?
So the diameter is 16.3.
That's supposed to be 1.6. So,
Because that's the diameter.
yeah.
0.163, so 0.08.
Oh, yeah, that's right.
No, it's right.
It seems right, doesn't it?
It is right.
You guys gave me the right numbers for shear modulus, and shear modulus was 10 times 10 to the 9th. Is that right?
For hardwood,
Yeah.
did you times it by point?
Yeah, I did, by 0.46.
It's,
Oh my gosh, I
It
hate
would have
that.
to be something that you did in both problems too.
Yeah.
So
yeah. Mine was also off with that.
Well, so maybe it is the question then. Okay. Yours is off by a factor of 10?
Yeah.
Okay, that's got to be it. I think when I did the conversion in the problem, I must have done it wrong. So I'll fix that.
version of
Okay, for the second part though, so what does a guy wire do? Like you always see these guy wires attached to poles and things. What do they do?
so they just help keep it straight.
Yeah, they keep it straight by providing tension, right? So if we want to attach a guy wire that's going to be up there to offset the horizontal tension provided by the power lines, right? Does that make sense? So we know what the horizontal tension provided by the power lines is just the square root of 2 times the tension, which was 503, I think, newtons, times the sine of 78.5. That gave us the horizontal component of the tension due to the power lines. Well, now what we want to do is we just want to put a guy wire up there. Here's our guy wire. The guy wire is going to pull down at the top of the pole at some angle theta. It probably tells us that stuff, I'm guessing. 20 makes a 25.2 degree angle with respect to the pole. Right? And we want to pull down with a certain amount of tension so that the horizontal component of the tension provided by the guy wire is going to offset this, right? Does that make sense? So what's the horizontal component going to be?
We just stayed.
Yeah. It's just going to be whatever this tension is times the sine of 25.2, right?
Mm-hmm.
So T
And then
sine, we'll call that T sub G for the guy wire tension. Sine of 25.2 degrees, well, that has to equal this, right? To cancel it. Right? The magnitude has to be the same. Say it again.
Or about 19.
So you're trying to find what the tension in the guy wire is. Right. Once you find what the tension in the guy wire is, then we can just find, we can find the vertical component and add that to this vertical component to see how much it's compressing. Does that make sense?
Yeah.
Okay.
It's the force over the area equals